Okay, so hi everyone, my name is Amandine and today I'm going to present things about biomechanics and gait analysis and more especially about kinematics. So first, what you need to know is that biomechanics is the study and analysis of human emotion, but also forces acting upon human emotions. So it is divided in two subsections. The first one is kinematics, which is the description of motion without regard to the forces causing this motion. It implies displacement, velocity, and acceleration. But you also need to analyze kinematics, which is the forces that cause the body to move. It includes ground reaction force, work energy, like metabolic energy, oxygen consumption, and muscle activity. But today we're going to focus on kinematics. So here is a little explanation about how everything is linked. So to have a gait efficiency, like an efficient gait, you need to have a smooth passage of the center of mass. And to have so, you need the lower limbs to follow a normal gait pattern. As you can see on the left of the slide, the comb point is oscillating during walking, and it reaches its greatest height during the single limb support, and the potential energy is maximum and the kinematic energy would be minimum. And then this point is going to reach the lowest height that it could have, and the potential energy would be minimum and the kinematic energy would be max. And to have a normal gait pattern, you would need muscle activity and also oxygen consumption. So you can see here that kinematics and kinetics informations are linked together to have a normal gait pattern. So regarding kinematics, the researchers tried to define different stages of walking. And the most common one is the gait stages defined by Letter and Contini in 1967, which divided the gait in three phases: a development phase, a rhythmic phase, and a decay phase. And the researcher focused more especially on the rhythmic phase for gait analysis. They found that the gait pattern is really consistent between individuals during this phase. And then they define a gait cycle, which is something that can be repeated during all the walk. So here is an example of the gait pattern. And because it's consistent between individuals, they decided to normalize the time reference in percentage to be generalized to every single individuals. So here you can see that the gait is divided into two main phases. Here the stance phase and then the swing phase. This gait cycle is the gait cycle of a right leg. So the stance phase is when the right leg is in contact with the floor, and the swing phase is when the right foot is oscillating in the air. You can also see that each phase is divided into several periods. The first one, the stance phase, is divided into 3 periods. The first one is the initial double support. So you would have both the right and left feet on the ground. And then you would have a single limb stance with just the right foot on the ground. And finally, we would have the contact with the left foot on the ground and the right one. At 62% of the gait cycle, you would go into the swing phase, where the right foot is oscillating in the air. This phase is divided into 3 periods: the initial swing, the mid-swing, and the terminal swing. But to define and characterize this gait cycle, we would need to define some criteria. These criteria are the cadence, which is the number of steps in standard of time frame. It can be defined as step per minute. You also have the step length, which is the distance between the same point, for example, the heel, on each foot during a double limb support. So after that, you have the stride length, which is the dimension, the distance between two successive foot strikes of the same foot. And then you would have the walking speed, which is the average speed attained after approximately 3 steps. So it's counted as centimeter per second or meter per minute. But you have to be careful because these characteristics are directly dependent on the age and the size of the person. For example, the step length would be higher if the legs are taller. But how can we characterize this kinematics information? Some human motion measurements have been developed, and the most common one is the use of external markers on body segments. These markers can be passively reflective or actively illuminated, and these markers are registered with cameras. When we talk about body segments, we refer to the head, which is head, arms, and trunk, but also pelvis, thick, shank, and foot. For the gait analysis, the most important part will be, of course, the lower limbs, like the pelvis, the thick, the shank, and the foot. So it exists like really particular placement for the markers. They have to be aligned with particular body landmarks. And you need at least 3 points to have like 3 points non-collinear to obtain information of the 6 degrees of freedom of each segment, like the position and the orientation of the segment. Once you have positioned all the markers, you can make some mathematical calculation to define reference frame. So first you need to define a vector between the markers, for example, here the ankle. You need to define one vector between the marker of the ankle and the one of the knee, which is the first vector of the reference frame, the STZ. And then you have to define another one vector between this, the vector of the ankle, and the vector of the marker on the shank. Therefore, you will these 2 vectors will give you the plane YZ. When you have that, you can make a cross product between these 2 vectors and obtain the CTX vector. Once you have the CTZ and CTX, you can then do another one cross product to have the CTY. And this is how you can obtain the first technical coordinate system. But you can repeat that for the reference frame of the knee. Thanks to these 2 frames, you can compute the relative angle between adjacent frames. But what you need to be careful of is that these frames are not aligned to the joint, like the biological joint. So for the most precise method, you will have a calibration step in addition with other markers. And for instance, they add a marker on the toes and another one at the back of the hair. And thanks to that, you can like translate the technical coordinate system that you obtained previously to the anatomical joint, which is the SAX, SAY, and SAZ. So as mentioned previously, to describe a human movement, you need first a reference frame, but also the dimensions of the movement. I mean degrees of freedom. But you also need to provide the type of movement, which can be linear or angular. It exists 3 main types of movement in biomechanics. The first one is the planar motion. It's a motion in just one plane. The first one, the more common one would be the angular motion, which is a rotation around a fixed center of rotation. And the center of rotation is the point where the velocity is equal to 0. And to determine this center of motion, you would have to find the intersection between the perpendiculars of 2 distinct velocity vectors, of 2 different points, in fact. But when you're walking, you would have like a translation motion in addition to this angular motion. So the core is going to move. So you need to compute this center of motion to different time moment. So this point would be the instantaneous center of rotation. And you would have to compute it with 2 consecutive positions. as you can see on the right of on the middle, in fact, of the slide, you need to have like two consecutive positions. With these two positions and the 4 points that you can see, A prime, B prime, you can like find the perpendiculars of the two distinct positions and then find the instantaneous center of motion, which is almost at the knee. But you need to be careful because this method is really sensitive to the error of location of the points used. And if you have a really small displacement, the error will increase exponentially. But also, if you use larger intervals of time, you will have less accurate position of the center of rotation. So the other one type of movement is the rotational three-dimensional motion, which is just a rotational motion, and you will like identify the joint as a spherical joint with 3 degrees of freedom. So here you need to be careful about the sequence of rotation because it is extremely important. For the same amount of rotation, you would have like different orientation. On the right, you can see an example. First, you would have like a rotation around the axis of Z, then the axis of X. But if you do the same type of rotation, but in a different order, like you begin with a rotation around Z and around X, and then around Z, you would have another orientation at the end. But to avoid this problem, the researchers define a way to unify this rotation with the Eulerian angles. And the rotation between a fixed vector triad, which is fixed to the fixed segment, body segment, and the rotation of the moving one would be quantified with a rotational matrix expressed with Eulerian angles. So the last one motion would be the generalized 6 degrees of freedom joint motion, which is in fact the unconstrained movement in 3D space. So you will have like free translation and free rotations. The method to describe this motion would be to use the screw displacement axis, which is in fact the axis that define in the same time the rotation and translation along a unique axis. But this SDA would just give you 2 parameters regarding the 6 parameters that you need to define completely the motion. So you need to define the 4 others, but these information are given by the inclination and the location of the SDA. So to define, like to compute, in fact, the orientation of the SDA and the screw rotation, you would use, as previously, a rotational matrix. So here are some examples of motion curves in sagittal plane, because during Gait is the most predominant motion plane. The first one is the hip flexion, which is like the most simple motion of the lower limb joints. It can be approximated to a sinusoidal curve. Then you would have the knee flexion, which is you can identify, in fact, 2 phenomena. The first one, which is the shock absorber, and the other one would be the foot clearance. Regarding the ankle joint, it's the most complex motion in sagittal plane because it's not, you cannot like identify this motion to a sinusoid curve, and it's a bit complex. You have like 4 segments. The first one with a really small plantiflexion. Then you have the dorsiflexion with just the flat foot, which be like succeeded by a plantar flexion, and then a dorsiflexion. So for the computation of kinematic information, there are some limitations, like the accurate timing of 2-off is really problematic. Also, you have problems with the skin movements, which induce marker movement. And also the placement of markers are not accurate and reliable between laboratories or between specialists. So you have some research perspectives to improve these limitations. Some markerless measurements of 3D motions are currently developed. Also, you can use active marker with radio frequency active emitters to decrease the number of cameras needed. So it's more about the economy of hardware in this kind of method. And then there is a need for a better method for joint centers identification. Like I talked previously, is that to identify the joint centers, you need you can like use several markers at the bottom of the foot, or you can just define the center of rotation, for example. But you can also use CT or MRI scanning. So here are some examples of other methods. The first one would be to use accelerometers and numeral integrations to compute the angle position. So you can see here on the picture that they use accelerometers on the leg, and with this information that can in fact integrate everything and obtain the velocity and then the position, like the angle position. But another one method would be the markerless gait analysis, which can be implemented on open pose with a skeleton tracking. And it can be useful because you don't need to place markers or this kind of thing. So thank you for your attention. Do you have any questions?